Good morning, afternoon, everyone. My name is Rui Li, and I'm excited to present our work, Mitigating Cache Noise in Test Time Adaptation for Large Vision Language Models. This research is a collaborative effort from Beijing University of Chemical Technology and our partner institutions. In this work, we tackle a critical challenge in making large models practical. Their performance drop when facing new data distributions at test time. Today, I'll first introduce the motivation behind our work, then I'll detail our proposed method, CRG. After that, I'll walk you through our key experimental results, and finally, I'll conclude with our contributions and a summary. Let's start with a key observation. In test time adaptation, or TTA, there's a significant performance gap between few-shot methods, which have access to a few clean, ground truth labels, and zero-shot methods, which don't. As you can see in the chart on the right, the performance with just 8 shot labels is much higher. Our hypothesis is simple. This gap is primarily caused by the noisy pseudolabels that zero-shot methods are forced to rely on for their cache. And this hypothesis is supported by the data. When we analyze the cache used by existing methods like TDA, we see that the pseudolabel error rate consistently stays above a staggering 20%. This introduces a huge amount of noise into the adaptation process. This noise creates a core problem for current cache-based TTA methods. They build a cache of test samples to guide future predictions, but this cache gets contaminated. This contamination leads to 3 key issues: bias class prototypes, sensitivity to outliers, and critically, these methods lack a mechanism to model the underlying distribution of the features, which could help filter out this noise. So to summarize our findings, the high error rate leads to imbalanced feature distributions in the cache and causes class prototypes to severely deviate from the true distributions. This is the fundamental problem we set out to solve. To address this, we propose CRG, a novel framework standing for cache, residual, and Gaussian. Our goal is to build a reliable cache and mitigate the impact of these noisy labels. It's built on 3 core components. First, a more robust and comprehensive cache system, which we then align using our second component, learnable residuals. And finally, to achieve true noise robustness, we introduce our third and most important component, Gaussian discriminant analysis, or GDA, for classification. Here's an overview of the full CRG framework. It's built on these 3 pillars. We start with a robust cache, which is then precisely aligned by the residuals, and finally used for robust classification by the Gaussian model. Let's look closer at our cache. We maintain a positive visual cache using a priority queue that favors high-confidence samples. We also have a standard text cache. Importantly, we introduce a virtual negative cache. For any given class, its negative prototype is simply the average of all other positive prototypes. This is highly efficient and avoids the need to store extra negative samples. To properly align these different prototypes, we introduce learnable residual vectors. We optimize these residuals with a combined loss function that does 3 things. It minimizes prediction entropy, it pushes text prototypes for different classes apart, and most importantly, it separates the positive and negative visual prototypes for the same class. This brings us to the heart of our noise robustness, Gaussian discriminant analysis. Instead of relying on simple similarity to a potentially noisy prototype, we model the entire distribution of features for each class as a Gaussian. We estimate the mean and a shared covariance matrix from our aligned cache. The key takeaway is that by using the entire distribution, our classifier becomes much less sensitive to individual noisy samples or outliers. We evaluated CRG extensively using standard clip backbones. We tested on 2 main scenarios: robustness to distribution shift on ImageNet and generalization across 10 diverse datasets. We compare against strong baselines like TDA and DPE. On the distribution shift benchmarks, our method, CRG, achieves new state-of-the-art average accuracy on both RaiseNet and ViT backbones. We see significant gains on ImageNet, consistently outperforming previous methods. The story is similar for cross-dataset generalization. CRG demonstrates strong average performance, improving over the state-of-the-art on both backbones and setting new records on several individual datasets like EuroSAT. This confirms the robustness and adaptability of our approach. To understand why CRG works, we conducted a thorough ablation study. We start with the clip baseline. Adding just the cache and residuals gives almost no gain. This shows that the residuals need proper guidance. Adding our negative prototypes provides a small but important boost. The real improvement starts when we add the loss constraints, which are crucial for aligning the prototypes. But the most significant jump in performance comes from introducing GDA. This confirms its power in robustly handling noise for classification. And finally, the full CRG model combines all these components to achieve the best performance. The key takeaway is clear. Both guided prototype alignment and robust, distribution-aware classification are essential. And importantly, we achieve this without a significant computational penalty. Our inference time is comparable to prior methods like TDA, and the memory overhead is modest and practical for real-world use. So to summarize our contributions, first, we identified and analyzed noisy pseudolabels as the key bottleneck in zero-shot TTA. Second, we proposed the CRG framework, which is the first to integrate GDA and negative prototypes in this context for noise robustness. And third, we developed an innovative residual learning mechanism for effective prototype calibration. Well, in short, our work presents a new state-of-the-art framework for test-time adaptation. It excels by effectively aligning prototypes, modeling class distributions, and enhancing robustness. Thank you for your attention. I'd be happy to answer any questions.